Hi everyone. Today we're going to talk about matrix equations. And a matrix equation, this is really just what it sounds like. It's an equation that involves matrices. So maybe something like this, ax plus b equals c, right? And the idea with these is that each of these things is a matrix. Now in a matrix equation, it's often the case that we're going to be trying to solve one. And that means that the unknowns are themselves matrices. And I should just say as an aside, here matrices includes vectors because a vector is really just an n by 1 or a 1 by n matrix. And we'll see some examples of that. One thing to be conscious of all the time when you're thinking about matrix equations is the dimensions of the matrices involved. So for example, in the equation above, the ax plus b equals c, let me just space that out and write it down again. So if we have a times x plus b equals c, if each of these is a matrix, then they each have dimension, some rows by some columns. So let's just take for an example, let's say c is a 3 by 2 matrix. So you may remember back from the second module that if you're adding matrices, they have to be the same dimensions. And when you add them up, you'll get another matrix of the same dimensions. So kind of reversing that reasoning, if this matrix C is a 3 by 2 matrix, that means since it's the result of a sum, these two terms must also be 3 by 2. So that's fine. We can say B is a 3 by 2 matrix. And if we know the product of A times X is a 3 by 2 matrix, then we know that A has dimensions 3 by something, and B must have dimensions that same something by 2. Because then when we take the product, remember the interior dimensions have to match, and then the result will be a 3 by 2 matrix once we multiply. So this is the kind of thing that I'm talking about when I say pay special attention to dimensions. Now let's see an application that's going to be important, especially to us, that is looking at systems of linear equations as matrix equations. So here's a system of linear equations that I want to use as an example to think about this system as matrix equation or viewing it as a matrix equation. Now we're accustomed to writing down augmented matrices for linear systems already, so I'm trusting that all of you can do that. Now I want to think about it a little bit differently. So let me write down a matrix expression and then we can pick it apart. Okay, so take a second to look at this, and then what I want to do is I want to multiply out this 3 by 3 matrix with this 3 by 1 vector. And when we have a vector that's written as a column instead of a row, we call that a column vector. Okay, so let's take the product of these two things. So remember when we are taking the product of two matrices, to find the dimensions of the product matrix, we cancel out these interior matching dimensions. We know that the resultant matrix is going to be, in this case, 3 by 1, right? And then we know we have 3 rows, 1 column, and we need to fill in the blanks. To get the first entry, so that's row 1, column 1, we're going to use row 1 over here and column 1 over here. There's only 1 column here. And let me erase this for a second. So we're going to take the dot product of those two things as vectors. So we'll take 3 times x1 plus 2 times x2 plus 5 times x3. And then to get the second entry, we're going to use the second row and the first column, the only column. So we'll have 1 times x1 minus 1 times x2 plus 6 times x3. And finally, to get this last, the third entry, we need to take this third row and this column vector and take their dot products. So we'll have 0 times x1, 1 times x2, and 1 times x3. Okay, so that's the multiplication, and now we have our resultant 3 by 1 vector. And hopefully you recognize this column vector has entries that are exactly the entries on the left-hand side of these equations. So this column vector is exactly storing the left-hand side entries of this system of linear equations. Right, so this is the kind of thing that we're going to take advantage of, and we're going to use some of the theory of matrices and matrix operations to to solve linear systems of equations. So this thing right here, it's called the coefficient matrix for this linear system, and this column vector is our variable. It's a vector of variables. And now if we make another vector so we can store the right-hand sides of these equations, we can actually write down a full-on matrix equation. So this is 2, 14, and 0 are the right-hand sides of these equations right here. And now I can write down my real matrix equation. So I'm going to give this matrix a name. I'll call it A. I'm going to give this variable vector a name too. Call it X with the arrow notation above it. And this column vector I'm going to give a name to as well. I'll call it B. And again, when we have column vectors or row vectors, we'll often use that little arrow notation. So now our matrix equation is AX equals B. All right, so that is how we write linear systems as matrix equations. In the next video, we're going to start seeing how to solve them.